An RC circuit is one that has a resistor and a capacitor in series. And they are really good for pretty much any application where you need to have something that repeats at a set time interval. So things like pacemakers, where they have to go off at a repeated time, or if you have like a strobe light that you want to blink at a particular time, or if you want to do like a filter for frequencies. So you want signals that have a high frequency, for example, to be filtered out, or signals that have a low frequency, repeat more slowly. If you want those to be filtered out, you can use a resistor and a capacitor to do that. And the heart of what's going on here is you are charging and discharging the capacitor. So if we're charging it, for example, we might have a little circuit like this, where we have a battery, and then the current is going to flow up through the battery and onto the capacitor, charging it up. And the time that's actually going to characterize this, how long it takes to charge the capacitor up, is going to be dictated by a time constant, which we usually use tau, and it's equal to the resistor resistance times the capacitor capacitance. Now this isn't the time that it takes to charge fully. It actually takes an infinite amount of time to charge this up fully, but it does characterize how quickly it happens. So, all right, so say we've got this situation. We are charging the capacitor, so there wasn't any current on it at the start, and then we plug the battery in and the current starts going and the charge starts piling up on the capacitor. So if we look at the charge on the capacitor as a function of time, initially there's no charge on it, it's discharge, and then very slowly it starts building up and building up until it gets to a max value. So this is the maximum amount of current, and the time constant is such that when you get to this time tau, you are charged up at about 63% of the max. All right, now the equation that characterize all of this is this guy. Got Q max, all of that times 1 minus E to the time over tau, the time constant. And that's why this is 63%. When T is equal to the time constant tau, this is e to the negative 1, which is about 0.37. So 1 minus 0.37 is 0.63, or 63% of the maximum charge. All right, and Q max, well, we can actually figure out what that is if we remember how capacitors work. That is what the capacitance is, and then just to get it down, we also have Ohm's law for the resistor. So when the capacitor is completely charged up here at Q max, the current actually goes to 0 because it can't push any more charge on the capacitor. It's completely charged up. So there's no voltage drop across the resistor. Current 0, so nothing's going across the resistor. So all of the voltage of the battery is actually over the capacitor. And so if you look at Q max is going to be equal to the capacitance times the voltage of the battery. All right, so that's the charge on the capacitor. If we want to look at the current through the circuit, well, that's going to start up at some maximum value, and then it's going to decay off to 0. So it starts going really, really fast when you first plug it in and there's no charge on the capacitor. It's at some max value up here, some initial value, and then it dies down. And if we look at if we look at the time constant here, that's when it gets to 33% of the maximum current. And the equation for current, well, remember current is the derivative of charge with respect to time, and that ends up being the initial current times e to the time over the time constant, where the initial current is equal to the voltage of the battery divided by the resistor, because initially there's no charge on the capacitor, so there's no voltage across the capacitor. All the voltage is across the resistor. All right, and finally, we can talk about the voltage of the capacitor. As I said initially, where we're at the maximum current right here, and then there's no charge on the capacitor, so there's no voltage across the capacitor. We start here at 0, and then it gradually ends up to whatever the maximum voltage here is. Same kind of time constant behavior going on when we hit t is equal to tau. We're at 63% of the maximum voltage, and the maximum voltage here is just going to be the voltage of the battery. When the capacitor is completely charged up, that's because it has put as much charge as it can, the current stops, and the voltage of the capacitor is equal to the voltage of the battery, because there's no voltage drop across the resistor because there's no current. So that is a capacitor charging up. Next, we'll talk about what happens when we take the battery out and we let the capacitor discharge. All right, so now we have attached the resistor and the capacitor to the battery. The capacitor is fully charged up, has as much charge on it as it can handle, and we just take the battery out and we connect it with the wire here. So now we're starting with a lot of charge on the capacitor, and without the battery there, the charge is going to start bleeding off, and that's going to be the thing that creates a current. So now if we graph the current on the capacitor versus time, we're going to start off with whatever our max, let me move this up here so I know that's the axis and not the value, whatever our max current is, and we're slowly going to bleed it all off until there's no current left. Of course, we never actually get to zero. We never actually get to zero charge because it's an exponential process, so it'll take an infinite amount of time to completely die off, but we get there pretty close. And of course, the time constant is the same. When we hit the time is equal to the resistance times the capacitance, that's when we're down to 37% of our maximum charge. And the equation for this is just whatever max charge we started at, the initial charge, it's that times this exponential decay. Again, and how fast we go depends on what the time constant is here. All right, and then the current, if we look at the current through the circuit, so I here, we're actually going to start negative. Wherever our initial current is down here, it's going to be negative. And why is that? Well, remember, current is the derivative of charge with respect to time. And when we take the derivative of this, we're going to get a negative there. So that will be negative Q over the time constant e to the negative t over tau. And it turns out this current here, that's the initial Q, this initial current is equal to whatever the initial charge is divided by the time constant. And then it's going to die away off to zero, exponentially decay. And the negative here just tells you that the current is going the other way. It is reversing directions from how it was when we were charging the capacitor up. And then finally, we can also give off the voltage across the capacitor. That is going to start at the max initial voltage and then decay off as well. And the equation for that will be the voltage with respect to time is the initial max. I guess we'll sort of do that, the initial voltage, and then it will be e to the negative t over tau. And if you don't know how these equations are derived, watch the next video and I'll show you how we get them using Kirchhoff's loop rule.